Hello students, Mr. Courtney here, and in this lesson we're going to be covering the electron configuration. And if we look at the word configuration, configuration basically means arrangement. So electron configuration, arrangement of electrons, and electrons are found in an atom, so we're going to be looking at the arrangement of electrons in the atom. We've studied the Bohr model of the atom, and we talked about just the levels, energy levels where we find electrons. And so today we're going to discuss in detail the arrangement of these electrons in the atom. So we first start off with Heisenberg's uncertainty principle. Heisenberg came up with the idea that was the death of the Bohr atom, where he said that it was impossible to know both the position and velocity of an electron at the same time. What that meant, or what it means, is that it's not possible to know the exact location of an electron at any given moment. So at any given moment, you cannot know the position of an electron. So this led to the idea that atoms do not, or they don't have Bohr orbits, where Bohr suggested that, I suppose this was our nucleus, that electrons were found in fixed orbits around the nucleus. So that became the death of that. Now the orbits, what Bohr called the orbits, they became known as an area where there is a probability of finding an electron. And that probability was defined as 90%, and we'll see that in a bit. Okay. So Schrödinger came up with an equation that described both the location and the energy of an electron in an atom. So he determined that there is a high probability, or 90% probability, that an electron will be found within an orbital in a certain energy level, or in a sublevel and energy level. Now, the model that was based on his proposal, on his equation, is called the quantum mechanical model, and this is the model that we use today. Okay, so this is the model that we use today, the quantum mechanical model, based on the equation put forward by Erwin Schrödinger in 1926. Now, some helpful things. An atom has 7 energy levels, or quantums, and this is going to be, pay attention to this here, because later on we'll see where we've already met this, where we know this from. Now, each energy level can be further divided into what are called sublevels. So think of this. So, not very good at drawing, but we have school, or we have 2 levels in a house or school, wherever you want to put it. On each level there are different rooms, but all these rooms make up the level. So on the first level we have 1, 2, 3, 4 rooms. Let's say we go on to the second level, where we have 1, 2, 3, 4. So we have now 1, 2, 3, 4, 5. So we have five sub-levels. So on the first level, so everything here is on the second level, and everything here is still on the first level. So that's what we call sub-levels. Within an energy level itself, we have different sections, which we call sub-levels. And these sub-levels themselves are arranged into orbitals. They have their own orbit, which we're going to look at in a bit. So what are orbitals? Orbitals are 3-dimensional regions around the nucleus that describe the probable location of electrons. Remember, we said that in those orbitals there's a 90% chance of finding an electron. Each orbital can hold up to 2 electrons, and keep that in mind again, because we're going to need this a little bit later on. So in math and in graphs, and so we've done before, everything we've done has been in 2 dimensions. So just like this. Now we're going to do a 3rd dimension. So we're going to be doing stuff now, or we're going to be looking at in 3 dimensions. So we're going to have an x plane, and the y plane, which we already have. Now we're going to be introducing the z plane. So we'll be looking at stuff in 3 dimensions. When we talk about our orbitals, we'll be looking at the orbitals in 3 dimensions. Alright, so let's talk about our sublevels. We've mentioned these already. We have the S, the P, the D, and the F. The S is spherical, so here we're going to use a cloud to mean orbital. The P with dumbbell, or the P shape or peanut shaped. They're going to have 3 clouds or 3 orbitals. 5 clouds, 6 orbitals, 7 clouds, 2 orbitals. And I'm going to introduce this here, but we're going to be looking at it again in a few minutes. Now, if it has 1 orbital, we said each orbital can hold 2 electrons. That means the S sublevel can hold how many electrons? Did I hear you say it? Yes, 2 electrons. How about the P? 3 clouds or 3 orbitals. 3 times 2 would be 6 electrons. 5 clouds. 5 times 2 is 10. 7. 7 times 2 would be 14 electrons. So keep that in mind. You would need it later on in the video too, if you're going through the notes. Okay, so let's look at the S sublevel. S sublevel has 1 orbital. And as we said before, each orbital can hold 2 electrons. So that gives us 2 electrons maximum in the S sublevel. Now, in terms of their general shape, remember we said we're going to be introducing it in 3 dimensions. So here we're talking about our X plane, back to front, Y plane, let's say left to right, the Z plane or the Z plane, as I say Z where I'm from. We go from bottom to top, so that's what we look at. Now the general shape. So the general shape, you will see it looks circular in 2 dimensions, but in 3 dimension it will be spherical. So think of it being like a marble. Okay, so it's going to be spherical. It's going to be all filled out. So that's what our S orbitals will look like. Now the P sublevel. The P sublevel, sometimes we say peanut shape, has 3 orbitals. 3 times 2 would give us 6 electrons. And this one shows us now what the different orbitals will look like. This one is in the X plane, in the Y plane here, and in the Z plane or the Z plane. Now what would happen, what would it look like if we were to put all of these together? So I put the X here now. Now I'm going to put the Y already with the Z. So this is what they're going to look like together. So this would be not necessarily, you don't need to know this, but I'm just going to give you the information. X, Y, and Z, because I put all of them on one diagram. So it shows a 2p, X, Y, and Z. Alright, so the quantum model. This is what the quantum model looks like. Now take a look at the picture. Can you see the different orbitals? Okay, so let's start with the 1s orbital, which is this. The 1s orbital is this region, this spherical, or it looks circular region here. From the 1s, then we go to our 2s orbital. So all the circular shape one or the spherical ones would be our s orbitals. Then we have our peanuts in here, which will be our 2p orbital. Then from the 2p orbital, we move on out to our 3s orbital. Okay, so this is what the quantum model would look like if we were to put all of these together. The D sublevel, double shape, 5 orbitals, 1, 2, 3, 4, 5. 5 times 2 would be 10. Here's what you need to take from this. The main thing we need to know here is what it looks like. We have basically 4 lobes. It's going to be double shaped. So that's what we need to know. It is not necessary that you know the shape of these at this time, but you should be able to identify them if you're shown a picture of them. Okay. Now the F, which is very, very complex. Think of it like a flower, whichever way. 7 orbitals, 14 electrons. Again, just be able to identify it if you see a picture of it. So we're not going to go into detail about this one, because as we said before, this one is very, very. Okay, so electron configuration. Electron configuration, as we said before, is the arrangement of electrons in the atom. We're going to talk about our energy levels, sublevels, the number of sublevels in each energy level, the number of orbitals, and the maximum number of electrons we can find in each energy level. Energy levels, we give them the designation N. If I would put the marker on. So we give them the designation N. So N is what sometimes we call our principal quantum number. It tells us the number of energy levels. So N equal 1 means energy level 1. N equal 4, energy level 4. Now in the energy level, each energy level has a certain number of sublevels. In the first energy level, we have the S sublevel. Use a different color ink. Use a different color. Let's try green. Okay. So, as I was saying, we have the S sublevel here. So that means we have 1 sublevel. Now, as we change energy level, the energy level will contain this sublevels from the previous energy level. So as we go on to energy level 2, we will still have our S, but now we're going to introduce the P. So that makes it 2 sublevels. We go on to the third, we'll have our S and our P. Then we'll introduce our D, so we'll have 3 sublevels. What do you think we'll have in the fourth? Okay, you said S, P, D, and then we'll add our next sublevel, which is the F. So we'll have 4. How about the fifth energy level? We'll have an S, a P, a D, and F. And we never talked about this one. We may not even talk about this one, the G. But just know that it's there, and that's 5 sublevels. So if we look at the relationship between sublevels, the number of sublevels and energy level, we'll see that energy level 1, 1 sublevel, 2, 2 sublevels, 3, 3 sublevels, 4, 4 sublevels, 5, 5 sublevels. That means they're the same, they're equal. So what do you think in relation to N? What are we going to put here? Think about it. What are we going to put there? If you said put N, then you were correct because it's the same. Now let's look at the number of orbitals. How many orbitals do we have in the S sublevel? Yes, it is 1. In the S we have 1, in the P we have 3. So 3 plus 1 is 4. So we take the 4 for the S and the P, we add the 5 from the D, that gives us 9. The 9 from the S, the P, and the D, plus the 7 from the F gives us 16. 16 plus the 9 from the G gives us 25. Yes, I know we did not talk about the G, but it's 9. So what did we do? 1 to 1. 2 to 4. How did we get 2 to 4? How did we get 3 to 9, 4 to 16, 5 to 25 in relation to N? So there's some relationship to N. Now you notice 5 squared is 25, 4 squared 16, 3 squared 9, 2 squared 4, 1 squared is 1. So what we did here is that we said this was N squared. So the number of orbitals is N squared, relating to the number of energy levels. Now the maximum number of electrons. Each orbital can hold 2 electrons. So all we need to do is multiply the number of orbitals by 2. Makes sense, right? Because each one can hold 2. So this will give us 2, 8, 16, 16. Why am I saying 16? 18. My math seems to be a bit off. Okay, sorry about that. 9 twos are 18. 16 twos are 32, and 25 times 2 is 50. So we had n squared previously, and we multiply n squared by 2. So the maximum number of electrons is 2n squared. Okay. The way the periodic table is arranged, it shows you this. It shows you the arrangement of the S, the P, the D, and the F sublevels. So we see all the elements in this region here. They're going to be in what is called the S block. All these here will be in the P block. All these here are in the D block. And these here are in the F, as designated by the letters we see here. So that means when we add electrons, we're going to follow this general pattern. It's a general pattern we're going to follow to add electrons. And we'll talk about why we do that in a while. But if you look here, we go 1, 1. But this is, why is this here? We go 1s, but we can still add one more to the s orbital, which is here. So if we're talking in terms of electron configuration, then this element, which is helium, should really be here because it's still in the s block. But why is it placed here? Why is it placed in this group or this column? We'll discuss that a little bit later on, but keep that in mind. Now look at where our orbitals appear on the periodic table. We talked about this. This here represents the period. We have 7 periods. How many energy levels or quantums we had again? Yes, 7. So the periods tells us the energy level in which the elements fall. All these here would be in the first energy level. They would have 2. These will have 3, 4, and you should catch the pattern by now. Now look at this. We go 1s, then we go 2s. After we filled our 2s, we go to 2p. Then we go to 3s, then to 3p. Then we go to 4s, and then we go to 3d. Why don't we go to 3d before 4s? We'll see. We'll talk about that in a while. But look, the 3d orbital appears in the 4th energy level. So the quantum number for the d orbital is 1 less than the energy level in which it appears. So when we talk about the d orbitals, they're always going to be n minus 1. So that means if we're in energy level 4, any element here will have a d orbital that is 3. It cannot be 4. We're in the 5th energy level. The d orbitals will have a quantum number of 4. Look at where the f orbital comes in the 6th energy level. But the number is 4. The quantum number is 4. That means they are n minus 2. So whenever we get to the f orbital, or the f sublevel, sorry, and I think I've been saying orbital and sublevel kind of mixed up. I'm sorry for that. If I say S, P, D, and F, I'm not talking about orbitals. I'm talking about the sublevels, and these sublevels have their own orbitals. So if I kind of got you confused, I'm sorry about that. Okay, so let's look at some other stuff as we move along, and we will get back and we'll see more in more detail about these and how we put these on as we go, and what's the significance of the positions, more significance of the positions rather. So if we look here, we see there's the Aufbau principle. So the Aufbau principle. An Aufbau is a German word, and if I remember it correctly, means building up. German word that means building up. So we add electrons to occupy the lowest energy orbital that it can enter. So that tells us the 1s is the lowest energy orbital. Then the 2s. Once we fill the 2s, we go on to 2p. When the 2p is filled, we go on to 3s. Then 3p, then 4s, and then back to 3d. So the reason we fill the 4s before the 3d has to do with energy. If we say that we feel that electrons are added to the lowest energy orbital they can enter, and they enter the 4s before the 3d, what does that tell us? Okay, yes, that tells us the 3d orbital has more energy than the 4s orbital. So it's at a higher energy. It has a higher energy. More energy is required to enter the 3d orbital than the 4s. Same thing with the 4d. More energy is required to enter the 4d than is required to enter the 5s. And then we get to the 4f, we see the same thing. More energy is required to enter 4f than 6s. When we look at electron configuration, we're going to see some things that look like this. And it's important that we understand what this means. The number or the coefficient shows the principal quantum number. The letter shows the type of orbital the electrons are in, or the sublevel the electrons are in. And the superscript shows the total number of electrons in a set of orbitals. When we say total, what we mean, for example, we can have let's use the P. The P has 1, 2, 3 orbitals. So how many electrons in total do we have in these 3 orbitals? Do we have 1, 2, or 3? So it's not how many we have in per orbital, but the total number in this set of 3 orbitals. That's what we're talking about here. Okay, so let's look at writing the electron configuration for the following atoms. So we start with hydrogen. Identify hydrogen on your periodic table. If you don't have one, you should get one out, so you can pause the video, get it out. Hydrogen has 1 electron. So we're going to start according to the Aufbau principle, start from the lowest energy level. That is the 1s. So we start with 1s, and we have 1 electron. And that is all. That is our electron configuration for hydrogen. We do helium. We'll start with our 1s. Helium has 2 electrons. So we add our 2 electrons, 1s, 2. If I can make it look like a 2 properly. So that's our 1s, 2. Then we go on to lithium. Lithium has 1, 2, 3 electrons. So again, we start with our lowest energy level, 1s. We add our 2 electrons. We still have 1 more electron. So that means we go on to the next energy level, which is 2s, and we add 1 electron. So lithium is 1s2, 2s1. Boron. So we look at boron now. Boron is here. Boron has 5 electrons. So again, we start with our lowest energy level, 1s. We add our 2. We add 2, but we still have 3 electrons to add. We go on to the next energy level, 2s. And in that sublevel, we can add 2, but we still have 1 more. So now we're going to go into this region here. Remember, this region is the P block. So this is the P block. So we enter the P sublevel here in the second energy level. So 2p. We've already added 2, 4. All we need to do now is add 1 electron. So that gives us 1s2, 2s2, 2p1. That's our electron configuration for boron. If we do the same thing for oxygen, oxygen has 8 electrons. So we start at the lowest energy level, 1s2. 2s2, so that takes care of 4 electrons. Now we need to go into the p sublevel, and we have 4 electrons remaining. The p can hold a maximum of 6, so we can add our 4 electrons here. And if we add our electrons together, 2, 4, and 4 is 8. So that is our electron configuration for oxygen. Now, another way of looking at it is this way. First element in the first energy level, that is 1s1. Go across to helium, second element in the first energy level, 1s2. Now, our first energy level is filled because it has one orbital that can hold 2 electrons. So we're filled, and we get to the end. We need to move on to the next energy level, 1s2. Then we come to the first sublevel in the second energy level, which is 2s. But we only have 1 electron to add to it, so we get our 2s1. Again, 1s2, 2s1. When we go to boron, we fill 1s1, we fill the 1s sublevel, so that's 1s2. We fill the 2s sublevel, so that's 2s2. Then we start filling the p sublevel in the second energy level, 2p, but we only add 1 electron, so that gives us our 2p1. Oxygen, 8. So that's our 1s2. First energy level is filled. 2s2. The s sublevel is filled in the second energy level. 2p1, 2p2, 2p3, and 2p4. So that's another way you can look at doing it. Okay, so let's look at the electron configuration for neon. So we find neon on the periodic table, which is here. We realize it's in the second energy level. It's at the end of the second energy level. So that means the first and the second energy level are filled. So to write the first energy level as being filled, it's 1s2, 1 sublevel, 2 electrons in the s. We go into the second energy level, 2s2. So that's these two here. Then 2p1, 2, 3, 4, 5, 6, because the p can hold a maximum of 6 electrons. So 2p6, and there we have it, electron configuration of neon. If we look at the electron configuration of sodium, we'll see sodium comes just after neon. So we have neon, the next element, or the first element in the next energy level, or the third energy level is sodium. So sodium will look similar to neon. It'd be 1s2, 2s2, 2p6, because the first 2 energy levels are filled. Then we get into our third energy level, into the s sublevel, 3s1. So that's it for sodium. Okay, so now let's do phosphorus. Let's find phosphorus on the periodic table. Phosphorus is here, the P. Hope you can see it clear enough. If you can't find your periodic table, find it on your periodic table. It's here. First energy level filled, second energy level filled. So that means it's going to look similar to neon up to a point. So let's do this. We know it's going to be 1s2, 2s2, 2p6. Now we get into the third energy level. The s sublevel is filled. So that is 3s2. When we get into the p sublevel, it's 1, 2, 3. So it's a third element. So that is 3p3. There you have it, the electron configuration for phosphorus. Okay, so now we move on to calcium. So we find calcium on the periodic table. Calcium is here. It's in the fourth energy level. So that means its first, second, and third energy levels are filled. Let's see how we represent that. 1s2, 2s2, 2p6, 3s2, 3p6, 6. So that takes care of our first 3 energy levels. Now we need to get into our 4th energy level, and it's the second element in the S sublevel. So that means it's going to be 4s2. All right, now vanadium. Let's find vanadium. Vanadium, it's here. Ah, very interesting. Let's see how well you remember you paid attention before. So vanadium, it's in the 4th energy level. So that means its first, second, and third energy levels are filled. So it's going to look a lot like calcium with some other things added to it, or something else added to it. So if you write it out, it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now this is where it can get confusing. We get to the middle of the periodic table. Now remember, when we enter the middle of the periodic table here, we get into the D block. So if we get into the D block, 1, 2, 3. So it's going to be D3. Now I did not put the number in front, or the quantum number. So what should it be? If you said 4, you're not correct. It's incorrect. Because remember we said before, the D sublevel shows up 1 energy level later than it's supposed to. So if it's 4th energy level, it's 1 less than where it's supposed to be. It's 1 further down. So it's n minus 1 as we said before. So it should be n minus 1, which is 4 minus 1. So it will be 3d3. And there you have it, electron configuration. So now let's talk about valence electrons. Valence electrons are the electrons in the highest occupied energy level. These are the electrons that are involved in chemical reactions, and they define the chemical properties of an element. And it makes sense, doesn't it? Because if they're the ones that are involved in chemical reactions, then they are the ones that should define the chemical properties of an element. Now, how does that affect the arrangement of the periodic table? Earlier we talked about the periodic table in terms of the periods. And the periods we know represent our energy levels. So for example, calcium will have 4 energy levels. Rhodium will have 5. Oxygen will have 2 energy levels. But what about the placement in groups? Elements are placed in groups, as we said before, and we discussed this previously when we did the structure of the periodic table. Elements in the same group have similar, not same, but similar chemical properties, even physical properties. So they behave similar. They behave alike. And that has to do with the number of valence electrons. So all elements in group 1A will have the same number of valence electrons. And in our representative elements, with the A's, so 1A, 2A, all these here, our representative elements. In 1A, they're going to have 1 valence electron. In group 2A, 2 valence electrons. Group 3A, 3 valence electrons. 4, 5, 6, 7, 8. 8. That number 8 does not stick right in some places. Now look at this. Helium. Helium is in the first period. Helium has 2 electrons. There's no way helium can have 8 valence electrons. So why is helium placed in a group with elements that have 8 valence electrons? Think about it. Why do you think they're placed there? Sorry, not they're placed there, but why is helium placed with these elements that have 8 valence electrons and it only has 2? It has to do with the number of sublevels or energy levels. Helium has 1 energy level, so 1 sublevel, the S. How many electrons can the S sublevel hold? 2. Only 2 electrons. 2 electrons, that is filled. 10 electrons, 8 in the outer energy level, that is filled. So it has the maximum number of electrons it can hold. So its properties will be similar to that of these same elements that we call the noble gases. So hence the reason helium is placed in this group. When we get to these elements in the middle here, they're a bit different in terms of valence electrons. Transition metals can have multiple, some of them can have multiple number of valence electrons, and we'll talk about that, multiple charges. So we'll talk about all those later on too. Okay? Lewis dot structures or Lewis dot diagrams. It's just a neat way of showing the number of valence electrons in an atom. What are valence electrons? Electrons in the outer energy level, or the highest occupied energy level. So the electrons are represented by dots. So for example, hydrogen. Hydrogen only has 1 electron, or 1 valence electron. So this will be the correct Lewis dot structure. If we were to do one for, let's say, sodium. Sodium is also in group 1. So sodium can have 1 valence electron. Now, in terms of the placement of our dots, some texts will tell you there's a specific order, and on the notes we said put the 1s at the top, but it doesn't matter really. You know, it really doesn't matter. You can start by putting your s's at the top. So if we went to sodium, let's go to, let's say, calcium next. Calcium is in group 2. So if we go based on the notes, and the notes say put the s's at the top, calcium would have 2 valence electrons. So we just put the 2 dots at the top there. Okay. Let's say aluminum. Al. Aluminum would have 3 valence electrons. Check on your periodic table, group 3A or group 13. So we put our 2 s's here, and then we can put the p's on either side. So that's aluminum. Let's do chlorine. Chlorine will have 7 valence electrons. We put the 2 s's. 3, 4, 5, 6, 7. We can do that way. Like I said, the order is not that important as of now. What matters is that we show the correct number of valence electrons. Alright, so let's look at the noble gas configuration. Noble gas configuration has to do with noble gases. If you guessed that, yes, you're correct. Noble gas configuration is a shortened way or shortened way of writing the electron configuration of the elements. Now we need to know that noble gases have their all their energy levels filled. So for example, helium, neon, argon, krypton, xenon, and radon, they all have their energy levels filled. So any element coming after them we can use these noble gases to substitute for the electron configuration of that element up to that point. And we use germanium as an example. So germanium is here. When we say germanium, we find the noble gas before germanium. So that's one of the previous energy levels. So we go up and to the end, which is argon. So that's noble gas. We place this in square brackets. Then we go to our 4th energy level. We fill our S sublevel, 4s1, 4s2. We fill our d orbital, and remember the d is always 1 less than the n, so n minus 1. So n is 4, so n will be 3. 3d 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Germanium is here. We get into the p, 4p, 1, 2. And there you have it. Now, in terms of valence electrons, how many valence electrons are we going to have here? We're going to have 2 plus 2, so that gives us 4. Does that make sense? Let's see. We say four valence electrons. So 4 valence electrons, that's what we're predicting. Look at its position on the periodic table. Group 4A or group 14. All these have 4 valence electrons. Okay, so let's look at some examples of writing noble gas configuration for elements. We're going to start with bromine. So first thing we do, find bromine on the periodic table. This is Br here. Go one energy level up and back up to the end. So that's argon. The noble gas before bromine is argon. So we write argon, the symbol for argon, and we put it in square brackets. Then we go to our next energy level, 4. We fill the S sublevel. So that is 4s2. Then we go across to D. So that's 3d10. Once we get to 3d10, we continue across into the P sublevel. P1, P2, P3, P4, P5, and that's still in the 4th energy level. So that is 4p5. Now, how many valence electrons do we expect this to have? Bromine is in group 7A or 17. We expect it to have 7 valence electrons. So let's see if do we have 7. 4, that's 2, and 5 gives us 7 valence electrons. So there you have it. Let's do barium. So let's find barium on the periodic table here. Find the noble gas before barium, which is xenon. So that's xenon, Xe. Then we go on to the next sublevel, energy level, which is the 6th, S1, S2. So that's 6, xenon 6, S2. And that's our electron configuration for barium. Okay, so our next element is palladium, Pd, which is here, element number 46. So we find the noble gas before palladium, which is krypton. We're going to do the same thing. So that is Kr in parentheses. We go to the next energy level, which is 5. So that's 5s2. We go across the D. And remember, D is always going to be 1 less. So we go 1, 2, 3, 4, 5, 6, 7, 8. And since D is 1 less, remember, it's 4D8. Now let's do lead. Let's find lead on the periodic table, Pb. So Pb is here, element number 82. The noble gas before lead is xenon. So xenon goes in parentheses or square bracket. Xenon. Then we go to our next energy level, which is energy level 6. And sorry, it's kind of written over here. So energy level 6. So that gives us 6s2. Now be careful, when we get here, we need to get into a F sublevel. And the F sublevel shows up 2 places later than it should. So it's n minus 2. So we go into 4f14, since we go across the entire length of the F sublevel. Then we get into our P sublevel, which is going to be the 6p. And it's the 1, 2, the second element, so 6p2. And that's we have our configuration for lead. Now, in terms of valence electrons, again, how many valence electrons do we expect to have in lead? Lead is in group 4. Let's look at our valence electrons. 2 plus 2 is 4. Sorry, I made a mistake here. I forgot, totally forgot something. and it's not allowing me to erase this, so I need to take this out. Sorry, I forgot to put in my 5D10. So I forgot to put in the 5D10. So if you caught that, very good, very good. So I forgot to put in the 5D10. Now I put in my 5D10, then I go to 6P2. And that looks like the correct thing now. So again, my apologies for that. Okay, so this takes us to the end of writing electron configuration. So we talked about Heisenberg's uncertainty principle, how him and Schrödinger redefined the model of the atom. We looked at the arrangement of electrons, which is electron configuration, the number of sublevels, orbitals, and maximum electrons that each energy level can hold. Okay, so these are some of the things we looked at. We looked at how to write the electron configuration for elements. We looked at how to get the number of valence electrons. We looked at drawing Lewis dot structures, although we did these briefly, but you can go through these. We'll discuss it again in class or in more notes, more practice. So we got valence electrons, Lewis dot structures, the shortcut method, which is the noble gas configuration, which is the last thing we did here. So again, I really hope these videos are helpful to you guys and you find it useful. So until the next video, I'm out. Bless.